Hello, welcome back to NMI. In the previous video we saw the designing and building of a very unusual Commodore 64 power supply, one that does not need a bulky transformer. In this video we are gonna test that power supply on two Commodore 64s. So let's go. Warning: the design you're about to see is experimental and not certified in any way. There are several areas of this circuit directly connected to mains, 120 volts AC, and that voltage can hurt you badly or even kill you. Do not try any of this if you are not sure of what you are doing and understand the risks. On my previous video, we saw the first testing of the power supply, and we could see it working, and we could see the waveforms on the scope and the voltage, but that was all. We did not have time to test on the actual Commodore 64. So in this video we're gonna take a look on two machines using the power supply. The first one is a test subject, let's put this way. It's a non-functional Commodore 64 that I got from friends. Thanks Daniel and Herc. I use that machine because I can remove all the chips and test it. It's non-functional anyway, but most of the logic and memories are there, so the current draw is there. And the other machine that I am gonna use in this video for testing is the Commodore 64 that is behind me, that C64. So in this video we're gonna see the power supply working with two machines, and hopefully everything is gonna be fine. Okay, so now we have our Commodore 64 here. That is the motherboard, right? I removed all the major ICs, including the VIC-2, SID, CPU, everything, right? To CIA, ROMs, and everything. Now, power supply is connected here. I have the scope measuring the AC input. My power supply is here. Everything is unplugged. And now we can power it on and see what happens. Again, fingers crossed. Okay, we can see on the scope the voltage. Everything looks okay. Yeah, I didn't switch the power on the C64 yet. One thing that I want to show you, the max voltage 12.2, 12.8, 12.4 there, right? Maybe we can move this one here. Is this gonna help? No, let's leave it there. Okay. But yeah, we can see the voltage is the same that we measured before. Now let's power it up. But when we switch power on, now we can see that the voltage fell a little bit. But now that we switch it on, we can see that the maximum voltage fell to about 11.2, 11.0 volts. So that is within what I was expecting. And it's good news because we don't see any smoke yet, right? Let's measure now some key voltages. First, this is ground. Let's see the output of this. Is this the right one? Yep. This is the regulator for like the higher voltage, and we can see that instead of 12 we have 11.98, which is pretty good, right? The input here is what? 18 volts. Now I'm gonna switch power off because I want to move this probe. Let's move this probe so that we can see some of these waveforms. Are we gonna see anything here? Not too sure. It's mostly AC, mostly DC, sorry. Yeah, as I mentioned, it's mostly DC and 18.8 volts max. We don't see any ripple. You should see maybe some peaks there, but no, it's mostly DC, which is good because this is what the capacitor here. Oh yeah, this is 470, yeah, of course, and that's also 470, but that is part of the voltage doubler. And this is the capacitor that filters out, or yeah, gets the DC. What else? We can maybe here this 2200. Oh, this is for the, okay, this is the 5 volt, that regulator, the 5 volts there. And we see what? 9.6 volts there. Which is also good because this regulator expects 5 volts plus the internal voltage drop, so we must have something higher than 5 volts. Around 7-8 volts is the minimum. We have 9.6, which is good. Let's also take a look at the 5 volt rail that is coming from the power supply. 505, yeah. Again, we were measuring 514, I think, and this small drop is because of the loading now. That is expected, and it's pretty good, to be honest. Let's see if we can see the waveform on the doubler. Oh yeah, see, this is the voltage doubler. Yeah, so we have peaks of 19.6 volts there. I want to show you something. Let's, now that we have, let's where is that? Save. Can we save this waveform? Reference chat. Let's see if that's gonna work. Yeah, let's turn it off and see if we can recall. Oh, here, reference menu. Cool, yeah. So now we have a reference there, which is the waveform that we were seeing here. What I'm gonna do is I'm gonna unplug this power supply. And I'm gonna plug the original power supply. And then we can compare. Oh, so many wires. And then we can compare the outputs. Okay, now this is one of my original power supplies. And we're gonna plug it in. here. Everything is the same here. Now let's turn power back on. Ah, see? That's what I'm talking about. Can you see how much higher the voltage is? That's pretty interesting, right? So, because this is AC and that is a transformer here for the AC part, the peak is higher, right? On 9 volt RMS, it's about 12 point something, 12.6 volts, I think. And so the doubler is gonna double that, and we should see about 25 volts instead of the 18 that we were seeing before. So if we go here and we go to measure, see, oh, 28 volts. See, so what does it mean? What happens here is that you're putting a lot more stress on this regulator here. This 12 volt regulator, it's a linear regulator, right? So it has to turn. So the difference between input and output, it has to dissipate that as heat, right? And in this case, there's the larger difference between input and output, means that it's gonna have to dissipate more power as heat, right? So there's more stress on this 7812. When we compare to the previous, well, my version here of the power supply, which by no means I'm not saying that it's much better or worse or whatever. That's just an experiment, but we can see that the voltage here on my power supply is only 18 volts, which is more than enough to feed the 7812, and we can measure the voltage output here on the 7812, and we should see also, yeah, see, exactly the same voltage that we were seeing with my power supply, 11.98. And if we look at the 5 volt rail, what are we gonna find here? This is the one that usually fails on these power supplies, by the way. 5.0402, yeah, it's good. So there's no problem with this power supply, but it can fail at any moment, right? I hope it doesn't fail now, but it can, right? So, and when it fails, the failure is catastrophic. Usually the regulator shorts, and then you get a lot more voltage on these circuits. Instead of 5, you're gonna get higher voltage, and then you're gonna fry everything, right? Well, everything that is connected on this 5 volt. So everything that is on the 5 volt can, the plus 5 can, that is safe because it comes from this other regulator here, right? So amazing, good news. It seems to be working fine. Of course, we don't have the full loading yet, but I don't think it's gonna be a problem. There's one other thing that I want to show you. One of the side functionalities of the C64 power supply is the generation of a clock reference for the time of day circuitry that is in one of the CIAs. I think it's this one. I mentioned that in my previous video on the Commodore 64. So we need to make sure that the clock is correct on that circuit, right? So I have everything again assembled. I honestly had disassembled it, but I want to show you. So here we have the system with my power supply. It's plugged into the AC. I'm gonna turn it on. And just to make sure, let's see, make sure that we have the right voltage. So I'm gonna check the 12 volt regulator, measure. So 12 volt here. We have 12.6. We should be seeing, yeah, the voltage there. We should be seeing, yeah. Okay, 5 volts. $12 volts. And the 5 volt can. Cool. So now let's take a look. We don't need the multimeter anymore. Now let's take a look at the voltage. It's pin 11 of U27. So this guy. Ah, how beautiful. See? That is our perfect square wave in the frequency you can see there, 60 Hertz. So that's exactly what the time of day circuitry expects. So okay, just wanted to show you this. Now we're gonna test it on the real Commodore 64. Okay, now it's the moment of the truth. We have my functional Commodore 64 here. The power supply, my power supply is over there, connected to the machine. I did not plug it yet into the AC outlet. So wish me luck, fingers crossed. Let's see what happens. Okay, we have power. I can see the 2 LEDs there. Oh yeah, I connected a video cable here to that monitor, but that monitor is composite input only. So I am only using the Luma output from the Commodore 64. That means that we are not gonna see color image, just the black and white image, but that should be good enough. Again, fingers crossed. Let's turn it on. Yes, we have the basic Commodore Basic there. Oh, that is good. Okay, so the machine is working. It's responding to commands. Let's type quick basic program just to make sure that everything is working fine. The keyboard is not really good. And in my PSU, it's working. Okay, let's measure now. I'm gonna bring the multimeter. Let's measure the voltage outputs on the PSU. So we have the 5 volt and we are getting 5 volts exactly. Okay, now let's switch to AC and take a look at the AC output, and we have 9.8 volts AC. Pretty good. Yeah, I'm happy with this. So the machine is working very well, very fine. What else can we do? Well, I could try the data set, but I don't want to connect it here. Maybe we're gonna do that at another time, but I'm happy with the power supply. I think it's working as expected, and the design, at least the design proves that it is possible to replace the transformer and to synthesize an AC waveform. That's it for today. I hope you enjoyed this video. This power supply is not done yet. Well, I am not done with it yet. I see a lot of points that we can improve. The basic concept I really like. The fact that we can get rid of the 9-volt transformer. Maybe the next step will be to use PCB modules. I found, thanks to a friend, I found modules that we can use and build a small PCB with everything on it instead of using external power supply modules. I'm also gonna consider getting rid of the AC synchronization and using a microcontroller to generate the 60 Hz clock for the fake AC, and maybe we can add a few more features, and then we're gonna have a really cool and really unusual power supply for the Commodore 64. Anyway, thanks for watching and see you next time. Bye.